So let's do section 19.3 worksheet. And if you are trying to find this worksheet and you can't find it, where is this located? This is, for some reason, it is in your week 6 handouts. It's not in the week 7 stuff. So go find it there. 3 problems on this worksheet. First of all, write 3 equations for the rate of the following reaction in terms of the disappearance of each reactant and the appearance of each product. So we're being asked to write rates for the reaction, not individual, but for the overall reaction. So we want a reaction rate. In the reaction rate, that is where we include stoichiometry. So if you see the word reaction, that means you need to include the stoichiometry. If it just says, what is the rate of the disappearance of H2, then we wouldn't have to include stoichiometry. So we want for our reactants, the change in concentration needs to be a negative number so that we're factoring in that concentration is going to be, the change is going to be a negative number, and we want the negative sign in front to make the whole thing a positive number. The stoichiometric coefficients of both of our reactants are 1, so we don't have to factor that in anywhere. Our products always have positive delta, whatever they are. And since our product has a stoichiometric coefficient, we need to include that in the denominator of the rate calculation. So easy. Now write 5 equations for the rate of the following reaction. Again, that means we want stoichiometry. So for our first reactant, negative delta Br minus over 5 delta T, our stoichiometric coefficient, that is equal to negative delta BrO3 minus over delta T, that no stoichiometric coefficient there. That is equal to another reactant, so negative delta H plus over 6 delta T. And again, when we're doing these, our goal, if we're writing it for the reaction, our goal is to come up with a way of calculating the disappearance or the appearance of these different molecules that will be numerically the same for all of them. So that's why we are dividing them by their stoichiometric coefficients. And that's why we are putting negative signs in front of the reactants, because they are being used up, so they have a negative rate. So there's 5 equations for the rate of this reaction. And now here's one more problem. Considering the reaction, if H2 is reacting at a rate of 0.074, so this is H2's rate. This is not the reaction rate. Doesn't say the word reaction in there. At what rate is N3 being formed? At what rate is N2 reacting? So again, these are all not reaction rates. These are individual rates. So we can say for H, which is H2, which is a reactant, we can say negative delta H2 over delta T is 0.074 molarity per second. And again, we're not including stoichiometry in this because this number, 0.074, is not a reaction rate. It is specific to H2. If we want to go from H2 to NH3, we have to figure out how those two are related to each other, and that is the reaction rate. So this is where we're going to be bringing in stoichiometric coefficients. The rate of H2, negative change in H2 over 3 times the change in time, is going to be equal to delta NH3 over 2 delta T. So this reaction rate is what allows us to go from one individual rate to another individual rate. And we are going to take our terms, negative delta H2, negative delta H2 over delta T. That is equal to 0.074. So we're going to plug in 0.074 molarity per second over 3. That is equal to delta NH3 over 2 delta T. We are trying to figure out, our goal is to figure out delta NH3 over delta T. That is, at what rate is NH3 being formed? So that's this term right here. That's this term right here. So now we just need to do some algebra. Get that 2 out of the way, multiply both sides by 2. And that's going to give us this number, 2 times 0.074 over 3. The units will be molarity per second. If we want to figure out the last part, at what rate is N2 reacting, we're again going to use the reaction rate as the go-between. So we're going to say for this, the rate negative delta H2 over 3 delta T is equal to delta N2 over, what's our coefficient for N2? Coefficient is 1, delta T. And again, negative delta H2 over delta T is 0.074. So that's negative delta H2 over delta T. .074 molarity per second over 3. We are trying to figure out delta N2 over delta T. That's the rate of just the N2. Delta N2 over T is right here. We can just ignore the 1. Delta N2 over delta T. So this is 0.074 over 3 molarity per second.